Hello, welcome back to a new video. In this one, we're going to derive the Heisenberg uncertainty principle, but first we're going to show a quick construction of what's called the general uncertainty principle for two Hermitian operators. We'll call those Hermitian operators A and B because they're just arbitrary Hermitian operators, and they obey the following equations. So if we have a change in A, that's what delta stands for, a change, and we square it, we get the following equality. This is the expectation value of A minus the expectation value of A. This quantity here, or this difference here, is all squared within this outer expectation value. Same thing for a Hermitian operator B. The change in B squared is equal to the expectation value of B minus the expectation value of B squared. And then we close that outer expectation value there. And so from this, we get the fact that the product of these changes for A and B, so delta A and delta B, is greater than or equal to 1/2 the modulus of the expectation value of their commutator. This commutator here is called a Lie bracket. So we take the modulus of the expectation value of that Lie bracket, divide it by 2, and then we get the product of their changes. So this is called the general uncertainty principle because this is non-zero. Okay, so within this we're going to look at a classical case as well as a quantum case. So in the classical case, we'll just write it out here, classical case. We want to find out what delta x and delta p are. The change in position with the change in momentum. Well, this would be greater than or equal to 1/2 the modulus of the expectation value of the commutator for position and momentum. Now, we don't have to take the modulus of an expectation value, and the reason why is this. Our classical position observable is just position itself. That's pretty nice. And momentum, P, is equal to mass times velocity. And mass times velocity is just mass times the derivative of position in respect to time. This derivative here is the calculus definition for velocity. But we don't have to take an expectation value of it because these are not Hermitian operators. This is already an operation. If we just had this derivative in respect to time, not acting on anything, then that would be a bare operator. But this is already a process that has been done, namely a process applied to position in respect to time. So that's not a bare operator, that's just a classical observable. So if we were to calculate the commutator for position momentum, which, by the way, under the definition of the Lie bracket, is equal to x times p minus p times x, well, that's just equal to x times mass times the derivative of position in respect to time minus mass times the derivative of position in respect to time multiplied into x. But these just cancel out and give us 0. So in other words, we get what's called a trivial case. Now, if this was, we write this out normally, we wouldn't write this as a Lie bracket because normally we would want to use a Lie bracket for the quantum case. So normally we use instead what's called the Poisson bracket for x and p, and this gives us the multiplicative identity. Also showing here that we have a commutative case. So these operators, or observables really in this case, since they're not bare operators, they commute. And so that's really nice. That's classical mechanics. And so therefore, delta x and delta p is greater than or equal to 0. And that is our classical case. And so in other words, the algebra of our observables is abelian because these things commute here. Now for the quantum case. For the quantum case, we want to calculate the Lie bracket for operators x hat and p hat, where x hat is equal to position and p hat, the momentum operator, is equal to minus I times h bar times the partial derivative in respect to x. Now these are considered Hermitian operators here because, especially look here, we have a derivative just kind of hanging out in the middle of nowhere. It's not acting on anything. It's something that is supposed to act on something. So instead of just calculating this bracket here, which would be x hat p hat minus p hat x hat, instead what we want to do is use the bracket itself to act on something, namely a wave function, which we'll call psi here. And so this gives us x hat p hat acting on psi minus p hat x hat acting on psi. So now let's go ahead and expand this. We have x hat, which is this x, and that's going to multiply into momentum, which has a negative I times h bar constant here, so we can pull that constant out front here. Then x with the derivative, the partial derivative, acting on psi in respect to x. And then we have a minus sign here going into momentum, but momentum is already defined in terms of a negative sign here. So we have a plus I times h bar. But now we have a derivative operator acting on a product, so we have the partial derivative in respect to x of x times psi. So in other words, we have to use the single variable product rule from calculus to evaluate this. And so what do we get? Well, we get negative I times h bar times x with the partial derivative of psi in respect to x plus I times h bar. Now the product rule from calculus tells us that we can go ahead and just put an x right here and then take the partial derivative of psi in respect to x plus I times h bar, the partial derivative of x in respect to x times psi. Well, this is really nice because we have minus a quantity, or minus this product of terms here, plus the same product of terms here. And so these here cancel out, those go to 0, and what we're left with is I times h bar with the partial derivative of x in respect to x. Well, that's just equal to 1, so we have I times h bar times psi. So this is non-zero. And so in other words, the commutator of the position and momentum operators is equal to I times h bar. So in other words, these operators are non-commutative. The algebra of observables is therefore non-abelian. And so here we go here. This is to imply that delta x hat times delta p hat is greater than or equal to 1/2 the modulus of the expectation value of I times h bar. But on a unit circle, I is the distance 1 from the origin, and so its modulus is 1, and we're just left with an h bar, so therefore delta x hat times delta p hat must be greater than or equal to h bar over 2. And this is the Heisenberg uncertainty principle. Now, if we used energy, for example, and then time instead of position and momentum, we would have delta E with an energy operator. Maybe it could be something like a Hamiltonian or something like that, with delta T as some type of time operator here, and that too would be greater than or equal to h bar over 2. That's another instance of Heisenberg's uncertainty principle, and we can keep going between two different observables and create more examples here, but I think you get the general idea. This is why the vacuum is constantly boiling with energy. It's constantly fluctuating. But because this is an emergent process of a non-commutative geometry, well, we as humans that approximate things using commutative geometries, it appears like particles are popping in and out of nothing, but in fact there's not nothing. There is just a non-commutative process that we can't see with the naked eye. And so we can see its influence on the commutative structures and the commutative geometries that we can witness, or the ones that we use to approximate. And so if you have a lot of nothing, or in other words, a lot of this non-commutative vacuum structure in between, say, hundreds of millions of light years of between galaxies, it's going to appear as if those galaxies are receding from us. And they are, because this is the pressure that establishes what we call dark energy. It's sort of a negative pressure, if you will, and this is what ultimately drives the expansion of the universe.